My name is Andrew Rieman, and today we're going to talk about the IR spectrums and the NMR spectrums of acetone. Now, the purpose of our lab is to use the IR and the NMR spectrums to help identify an unknown molecule, which today we're going to look at acetone was the unknown molecule. Now, IR and NMR spectrums, there's a few similarities and a few differences. They both measure the amount of electromagnetic radiation that is absorbed in the substance. However, the frequencies at which they measure those are different. The absorption by photon in the infrared region is the IR spectrum, and the NMR spectrum measures the absorption in a radio frequency. And what they both yield is the IR is going to yield the number of different types of H present and the relative number of those types of H present, while the NMR is going to yield all the different kinds of H that are present. So we're going to look at acetone's background just briefly here. This is the molecular formula. That in the middle would be an extra carbon. Acetone's molecular formula is C3H6O. Intermolecular forces present are going to be dipole-dipole and dispersion forces. It's a solvent. A liquid dissolves other substances. It boils at approximately 56 degrees Celsius, and it's used in a lot of paint strippers, nail polish removers, solvents, that kind of thing. Now, when we go to predict the IR spectrums, again, what we're looking for is the number of different types of H and the relative number of those H's. When we predict the IR, we're looking for the different types of H's present. We're going to determine all the functional groups, which we see are the CO, which the functional groups that we're looking for are either C single bonded O, CH benzene ring, CH single bonded C double bonded O, C to Cl, or C to Br. And the groups present in this one, as we can see, are the C double bonded to O and the C single bonded to H. So those are the two that we're going to look for when we look at the IR spectrum, when we actually look at the graph of it. When we're looking at the NMR, this is the one that's going to yield the different types of the number of different types of H and the relative number of H present. As we can see, there's only one type of H present in this molecule, so we want to see one peak when we look at the NMR spectrum. An example of one that, so the ratio on this is going to be 1. An example of the ratio that would be a 3:1 with multiple different types of H, as we can see, would be methane. It's going to have two different kinds of H's, and the ratio will be 3:1 because there's 3 H's bonded to a carbon and then 1 H bonded to the oxygen, so there's going to show 2 different peaks if we were to look at methanol. Now we're actually looking at the IR spectrum. Again, we want to see the C double bonded to O and the C singly bonded to H. Those two are going to appear within 1750 to 1650 and 3010 to 2800. You can see here, this is the first one. This is going to be the C singly bonded to H, C single bonded to H down here, and the C double bond to O right here, this arrow is pointing. Now, when we're looking at the NMR portion of this, we see one peak. The relative number of that peak would be 6, so that matches up with what we predict. Now, in the conclusion, we can look at both of these spectrums and determine that our molecule is acetone because the spectrums match up with exactly what we would predict they would. Any questions?